recording again, and I demoed how to construct a pipe, including a consumer or including a supply station. And I explained how the network is crafted in sisHYD, that we just show the supply or the return. Let me close down the dialog boxes for a moment so I can do them individually, or I can just close the central dialog box, which will close all the childs that are here registered, nodes and pumps, the remaining ones. So I close down the boxes. The create supply command is still active in the tool settings. Let me activate the edit object. The drawing is we can create several drawings. They are based on a template which defines how the drawing is labeled and how color and weight attributes are assigned to pipes. And the central dialog for this is the Configure Templates dialog box. In this box, all available templates are listed. You can have as number of templates as you want. And whenever you create a drawing based on this template, you'll press the green button in this box. This will create a drawing with the labeling, with the annotations and the color coding defined in network supply. Let me press the button and then explain why the graphic changes. And please have a look at the view title. As part of the view title, you find network supply. That is the name of the template. And in front of it, there is the label calculation. That is the computational result that is displayed in this view. So looking at the title of a view, you get the hint. This is about calculation, the scenario. When you have multiple scenarios like calculation, design, dynamic, whatever you choose here is then combined. So network supply, here we have design. When I create, I have to explain these buttons are the same. So when you close this dialog box drawing templates, this is the active template. You draw from here. Now you created network supply combined with the results from a design. So this is the toolbox with the scenarios that have been computed. Here I've set up 3 scenarios: calculation, design, dynamic calculation. And for all the different scenarios, you can have the combination of a template with the scenario results. We go back to result supply with the design. Looks like this. If I go with the normal computation, yeah, looks different. And this depends now on the color coding that has been designed. And let me review the drawing template and change its configuration. So I go back, open the drawing template dialog box. The box has at the top icons to create a new template, copy, delete templates, and to review template properties. So when you select one in the list, click the properties. It opens a dialog box now displaying the template name, result supply. On the left side of the dialog box is a list of categories. You can choose between nodes and pipes. And for nodes, in the node circle symbol, you can assign up to 6 labels. to annotate information. And in case of results supply, we put a label with the pressure in the supply at the top of a node circle. In the middle, you'll find the short name, and at the bottom, the pressure in the return. Let me zoom in to look at one of those nodes. So with the normal computation, we are at quite high pressures. It's 10 bars in the return, 18 bars in the supply. And that is because this is a network that has not been designed. So it's on purpose for this training and demo that the pressures are too high. By picking a different attribute from this list, you can change the labels. Let me maybe not change this one, but instead let me create a new drawing template and start from scratch. So I press the new button. And see, it gets the label new template. The node circle is blank. On the right side, no color coding table assigned, no weight coding table assigned. The same for pipes. Please note that at the top of the box, there is one field called position. There you find options to have a supply network drawing, or one for the return, or one for a third pipe. In Germany, so-called KLB. It's for the ventilation, and it is for three pipe systems. And in three pipe systems, you can have a pipe on a lower supply temperature, so different supply temperature levels. Yeah, three pipe, it has one return in common and one supply for the heating and one supply pipe for the tap water. So the motivation in history was that in summer times you would not use the heating part. And you distribute the flows for supply to two pipes. So in summer times you have still reasonable flow rates and flow speed in a pipe. Whereas when it's a combined pipe and there is no heating in summer, you get very slow temperature, very slow speed, and which means quite high temperature loss. And yeah, so you can, with sisHYD, you can also compute three pipe systems. By default in district heating, most users have two pipe systems. So, and when you create a new drawing template, the default is that a supply drawing is created. So let me assign labels. Let's do the drawing first when there is nothing. When I do the drawing of the new template, I zoom in. There is a blank square, no label in it. Let's start and, for example, put in here the name of the node. And do the drawing again. So recreate. It puts the label in the middle. And the difference between name and short name is that for the short name, we omit the last letter, which indicates if it's supply or return. So name will display 37V. It gets more prominent when I switch the position to return. Let me do this and draw again. Then you'll notice it took here this part of the network. And you will notice the difference, especially, no, leave that as is. Okay, so first I switch here back to short name. And I can also use the temperature in the supply, and let's put at the bottom temperature in the return. Let's recreate, and now you find at this endpoint supply temperature of 101.3 Celsius degrees and return temperature 50 Celsius degrees. How to get now color coding working? So first you have to select from the drop-down list color which attribute you want to color code, and let's go with the temperature in the supply. And once you pick the temperature, you can drop down the list and see if we already created a color table. There is one, but you are free to, let's pick it first, temperature, and recreate the drawing, and it gets a green color. Let's look up why is it green. Behind the color, behind the table name, you find an ellipsis button. I click the ellipsis button, and it tells me how this color table for temperature, label temperature, is configured. It's in units of Celsius degrees. It has 2 intervals. Whenever it uses blue color, whenever the temperature is equal or below 80 Celsius degrees. If it's above 80 Celsius degrees, it uses the green color. With this dialog box, you can create new color tables, and you can create new color tables that are applicable to attributes that are in units of cell that are temperatures. It depends on the attribute you choose what color tables are here offered. So if you have if you go to for pressure loss, we show only color tables that have the same dimension. If it's a color table for length, then you have only length color tables. And this is, for example, with the weight diameters. We'll see later. So, but first, let me create a new color table. Give it a new name. Supply temperature. By default, it starts with 5 intervals. You are free to remove or add new rows into the table. What you need to do is to enter values on the right side to complete the table. So for example, let's go with less or equal 50 is blue, up to 90 is green, 100, then it's red, or let's go from green to, let's go to orange. And if it's above 100, we want to use the red color. So in our case, when we switch to this newly defined table, we can expect that the node will display it in red. So I've set up the color table. Let's look up. I created one, it shows up here. So I switch to the newly created table. I recreate the drawing, and the node is displayed in red. If I would change this here to turquoise and recreate, shows up in turquoise because the temperature is above 100 Celsius degrees. So this is the principle applies to all color weight tables. For weight tables, it is quite similar. We do this for pipe next, but instead of color attribute, you have a line weight. Okay, let's go to the pipe. No label on it yet. For annotation, you find again the pipe symbol. We use 3 symbols or 3 labels above the pipe, 2 below. They are not stacked above each other. Instead, they are in a row and separated by a slash. So let's select as label the pipe short name. And yeah, we have, I think, a middle temperature, a medial temperature. Output temperature. Pressure. Ambient. Gauge pressure. So let's choose the supply temperature. It's the temperature of a pipe is always the middle temperature between start and end. So and you can also have the output and the input temperature. So that is the output temperature of the pipe, and I think the input temperature. And temperature of the pipe means just the middle value between the average value between input and output. And below temperature return. Let me draw and zoom out a bit so that we can find the annotation. And maybe the note is it's quite small here, the label also. Maybe we want to increase the labels in size. The mechanism to do it is to modify the scale at which we draw. The location of the elements will not change. The scale will just influence the size of the annotation. So if we go here to, instead of 1 by 500, I go to 1 by 5000. So it increases the text by 10, factor 10. Same applies to the symbols. So same spot in the network, but much larger symbols. If it is too large, yeah, okay, we go down to 2500. Okay, now we can read it. The motivation behind this scale is when you draw it now at a scale of 1 by 2500, we'll place, the nodes will then have a diameter of 10 millimeters, and the text will be 2.5 millimeters in height. So you can read it. If you use exactly this scale for printing, it can be read in the output. If you do instead 1 by 10,000 scale, then the text will be 2 millimeters divided by 4. So half a millimeter, that is, maybe with the magnification glass you can read. I cannot anymore. I need my glasses. So, but this is a very convenient way to adjust it to a size that is convenient for you for display. and to quickly redraw and get it in the right size for printing. Okay, so for the pipes, we assigned labels. Now let's also do a color table and the weight table. We'll do a weight table first. And what is typically used weight table for pipes is the pipe diameter with a weight coding. So we also go here for the inner diameter. It's not just diameter, it's inner diameter supply. We also have an outer diameter, which includes the insulation and the casing. But inner diameter is most important for pressure loss, so that is what is typically displayed here. And when you look at the drop down for table, it shows two tables, one for design, one for pipe diameter. I'll explain the design table later when we do a network design study. So I assigned the tables and let me redraw. And we find now that most pipes are drawn with a different weight. And the bigger pipes here are, of course, with higher weight, and the smaller pipes are drawn with a lower weight. We can also apply the color table for temperature supply again. And what you find now is the temperature, the table you just created for supply temperature, it shows up in this list because the dimension matches. So the table that is set up for Celsius degrees or Kelvins, that can be used for any attribute that is the temperature, that has the dimension of the temperature. So let's use it, and we can expect that when the average temperature of a pipe is now above 100 Celsius degrees, it will be red. If it's between 90 and 100, it will be orange. But I think since this is a terminal node, maybe we should adjust intervals. I would, let's see if we have pipes that are orange. I guess most of it is red, right. If we adjust our intervals, and let's say we put this one here to 105 maybe this to 102 Celsius degrees, we see a bit of a difference. Yeah, then we find some orange pipes. So there is quite a number of attributes you can apply. Some of the attributes are just for the return or for the supply. Whenever we color code, we only refer to the attributes the drawing is for. So if it's a supply drawing, you find in the list all the supply attributes. If it's a return drawing, all the return stuff. Some of the attributes are expect that a supply and a return exists. So for the differential pressure, for example, we need a supply, we need a node in the supply and in the return, a pipe in the supply and in the return. Then we can compute the difference between supply and return. The attribute is then just called differential pressure supply. It means then between the supply and return in this case. Okay, this is the quite important part which you will, I guess, regularly use to get an impression what's going on in the network. Okay, was from drawing templates. Let me quickly check. Yeah, some more information about the drawing template. We gave it a name. You are free to change the name in the template. For example, this was results, or we just call it temperatures. And when I redraw with temperatures, you will notice that the label of the view will change. So it's now results from calculation combined with the template temperatures is making up this drawing. If I look at the specific pressure loss, it looks like this. And maybe this leads us to the next topic, which is how to do a network computation, what is required, and also to the question how to design a network. When we look here at the drawing, when specific pressure loss is color coded, we find a few pipes that are really in red and in orange. I can look up the specific pressure loss color table here by opening the table. And if the pressure loss, specific pressure loss, is between 100 and 200 Pascal per meter, it uses orange. If it's beyond 200 Pascal per meters, it uses red. So I think for us in Germany, we typically design around 100 Pascal per meter. And what I was told is that it has some historic reasons. In the 70s, the people made this balance between laying cost and operational cost. And the conclusion was 100 Pascal per meter pressure loss is from the economic standpoint the best one. Maybe nowadays it is shifting a bit, but it will for sure not be that too far away. So we'll redesign the network to get rid of the very high specific pressure losses in these spots. The dialog box here of the drawing templates has on the right end a few columns. One is when you hover with the mouse over the title, you get a tooltip. One column is to show maps. So when I uncheck, sorry, it's still showing the map. Perfect. Wow. I have to check this. Should go away. Anyways, there is another option here to get rid of the reference display. There is the world symbol. That is for the background map, and you can easily turn it on and off. Another one is here for the so-called collision control. The collision control means when I draw at a scale, I can explain it here. So the pipe here in the middle, the labels at the top are missing. That is because the text would interfere with the start and end node. It does not fit in between. And if I turn off the collision control, the text is drawn, but it will be hidden behind nodes. And in other situations, maybe you have a lot of text laying over each other, and you can clean up by performing the collision control. And then it will only display text that fit on the screen. When you look here at the text at the top of the pipe, there is the short name, And second was for results, it's the specific pressure loss, 237.1. If I draw it here at a different scale, let's say 1 to 10,000, it's not sufficient. Let me use 12,000. At some point, the label at the end will vanish because of the collision control. Still in. Now both are gone. It's incredible. Yeah.
Calculation.
Okay, when I use 1 by 14,000, only the first part of the annotation is in the drawing, the other one is skipped. You will also note that certain nodes will be displayed reduced, and we look at the priority of nodes. It's defined by the number of connection types, of course. More important is if a consumer is associated with it. More important if a pump or a supply station. So let me zoom out to show the situation now. And you will notice that here the nodes with a demand, with a consumer attached, they are at higher priority in this case. And that, of course, the supply station is of the highest priority. We have one field that controls priority, and that is at the nodes. You can check here a box called never reduce, and that is a property that is just telling the graphics to keep the node at full size. So for example, let's exercise this. I use the edit object tool to open the dialog box for node K35. I click it. This is now K35, and I check never reduce. By pressing apply, I save these changes. The difference between apply and OK is this one leaves the box open. When I apply, it's changed. Oh, and it automatically redraws, so it updates. And OK will also close the box. And if I revert this, go back to never reduce, apply. Oh, come on. Maybe it really requires a redraw. But this way you have slide control over nodes you want to always display. So that was the second column. The third column is to display a legend. Let me check this for specific pressure loss and zoom out, because by default the legend is displayed on the right side of the drawing. You can just grab it, move it around, and next time it will be drawn in this position. The legend is drawn at the same scale as the other network objects. And here you find exactly what we configured for color coding and annotation in the drawing templates. So what we did tells you again here, symbols used, that we used pressure supply, okay, in this case temperature supply, that is for specific pressure loss. when we do the same for the one we just created for temperatures. Let's do this one, and let's draw the legend. This is what we increase a bit more, than you can read it. This is what we set up, modified here the intervals, temperature supply, temperatures, and first field is the short name, slash, second field temperature supply, with the unit we use. Yeah. The unit is pre-configured in sisHYD. We have one dialog box to modify the unit setting. That is under menu point settings. There's a unit groups, and there you can find a list of attributes and the unit we use for display and reporting and for the drawing. You are free to switch the unit whenever you want. What we do in the backend for the computation and for our database is we use SI unit standard. So all lengths are in meters, even the diameter. And if you want to display it in millimeters, you can configure it here. Or if you want to display in inch also, that's fine. It will not change the data in the backend. In this dialog box, you can, for input validation, you can also define limits. So this one would limit you to define diameters only between 0 and 2000 millimeters. Otherwise, it will stop you and do not let you enter stuff that is higher or lower. We have anyway sanity checks in with the log files, or if values are not visible, we warn the user in the log files. So for example, what you cannot enter is a pipe with a length of 0 meters. We cannot compute the pressure loss for it. So we'll state, hey, there is a pipe which has a length of 0, or if the diameter is missing, those situations. Okay, there are 2 more columns in this box, and one is to extend the drawing and to the supply and return position. Typically, district heating has a symmetric supply and return, but given the case you have a network which has additional return pipes or supply pipes, you want to see them, to visualize them in one drawing. You can do so. That is by checking this field. So, for example, this drawing here is now drawing of the supply, right? Yeah. Let me draw a pipe. And the pipe is in the supply and the return. Now I uncheck the supply, which means it is no longer existent in the supply network. I apply the change, and it will go away from a supply drawing. If the drawing is for the return, network return, let me open this one. Network return is for return. I create the drawing, and you can expect that the pipe will appear here again. There is the pipe. In order to get a display where elements that are not already in get also drawn, you can check this field here. And this will additionally draw the elements that have no symmetric counterpart, that are only in the return. And the last option is that you restrict the drawing to objects that have been computed only. So if you isolate parts of the network, they have no results. Maybe you want to get rid of them for the drawing. then you can check this field. Be careful, because when you construct a network and there are no results at all, the drawing will be empty, because it only draws elements with results when you check this here. So this is, it can have side effects. Let me, I removed results. Now it's blank. This option is restrict drawing to calculated objects. From the calculation result dialog box, I did not pick results. So now I have no results. If I have no results and I draw, nothing will appear beside the background map. If I uncheck, it's the network. Because I have no results, we do not apply color coding, especially if the attribute is a result attribute. We will only apply color if we have the result. Otherwise, we go with a black color. And once I pick a computation again, I recreate the drawing, it will apply the color coding. Okay. Okay, I think this is what I wanted to explain for the drawing templates. By default, the software uses the templates for drawings and reports across all projects you set up. There is an option, and please remind me later if that is interesting for you. You can have templates on a per project basis, so that for your city the templates are different from the templates you apply to your city.
Yeah.
Okay, then we'll have a look.
Okay.
So now we did the construction, looked at drawing templates. Next, let's have a look how to carry out computations and what is required. So once you have set up a network, you need a minimal set of input data to carry out the computation. And that is for all controllable elements. For the supply station, you want to specify the supply temperature. For pumps, you typically operate to keep the differential pressure at the network end at a certain level. And this information is entered via the controls dialog box. There you find at the top one more information, that is the pressure maintenance. When we carry out the computation, we need at least one node at a known pressure level, or at least, or in the network for pressure maintenance, maybe there is a medium pressure, a middle pressure between two nodes. That is the information to get one fixed pressure. And here in this system, let's have a look at the dialog boxes. This is now non-graphical data. There is no representation of these elements in the graphics. I have here a pressure maintenance at node K105R. And recall, with the right click, you get a context menu and you can show the node in the graphics. Come on. Oh, I thought it would jump to it. It's a return node. So let me edit the data set. wonder it's not finding the node. I'm wondering it's the intermediate node here. Yeah, anyways, this is KOY K105R. The pressure maintenance is here at the supply station in the return. It maintains the pressure at 3 bars. And other than that, in this network, we only have a single pump. And a pump is typically controls the differential pressure at the consumer or at some endpoint in the network that is far away from the supply station. The motivation or objective of this control is to keep the pressure of the supply at every point in the network above the pressure in the return, so that you can transport water from supply to return. If it's too close or if there is an intersection and return pressure is too high, you cannot supply in these points. So this is the definition of such a pressure difference control. It targets the supply pump. It controls the differential pressure at the consumer, and the consumer is the consumer VB36 in this network. Let's have a look where the consumer is located. Why is it refusing to jump in the graphics? Bummer. Sorry, I cannot explain at the moment why this is not working. It worked before. It's not. No. Let me close the project and reopen. Something went wrong. Okay, I was with the controls and with the differential pressure control, and I opened the consumer and the consumer is this point in the network. Oh, the screen is, it's behind. Oh, sorry. There seems to be quite some delay between when I speak and what you see between the laptop and the screen. So if it's too slow, please give me a signal and I wait. So this is the consumer, and at the bottom we have the supply station. So it's a long way through the network, and most likely this is the critical point. So point at the lowest differential pressure after computation. sisHYD has means to also control the critical consumer. It's not used here. This is a control which is only for the specific one. Here's another control that has been defined, that the pump should control the pressure at the consumer that is operating on the lowest pressure difference and maintain the pressure in this point at 0.5 bar. So you can define multiple controls for a pump, but of course in a single calculation scenario only one of the controls can be activated. And now we have a look at the calculation dialog box, the steady state calculation. And the steady state calculation dialog box, it is used to add the scenario specific information in the system. So with the components and the network layout, it's all the static data in the system. On a per scenario basis, the information is entered in the calculation dialog box. So here you find several tab pages that deal with different kinds of information. On the general tab page, we find the alternative to compute. It's the complete network. You can also compute parts of the network. Most important is the exterior temperature and the load factor. Load factor is, some call it diversity factor. It is the percentage of demand you use in this scenario. When we enter the network, we enter for consumer stations the nominal demand. That is, if they operate at full capacity. Typically, you operate not at full capacity for all the stations, but a reduced capacity. And that is typically around 70% for district heating network. So in winter times when it's cold and almost all consumers need heat, they will not all at the same time use 100% of their capacity. And that is why then you have a scenario that maybe is around 70%. So this is on the general tab page. On the right side, you find here some options. One of them is to compute the supply time, which is the time the water takes to travel from the supply station to the consumer. If the consumer is close to the supply station, it's only a short time. If it's far away, the longer it takes for the hot water to travel through the network to reach this point. We can do a network design. We can compute the pressure losses at junctions. So at the very beginning, we discussed pressure losses, pressure loss computation in straight pipes. But in the connection point of pipes, depending on if they are in a very steep angle or in a flat angle, and depending on the flow direction, you can have pressure losses in junctions. There are formulas to compute it. And some of our users use these formulas. Others go just with the length correction factor, which includes, or it does just ignore the pressure losses in the junctions. It would be included in such a correction factor. And one of our users is not using the length correction. They are using bends, and they use the calculation of pressure losses in junctions. And one option lets you turn off the heat loss computation. It's an option to get around convergence problems with the computation. There are situations I'll describe in the advanced course where there is no convergence. It calculates, and one of the reasons is here this formula. If we iterate and the temperature difference gets too small, it means high mass flow. High mass flow means that the water does not cool down, so it's alternating between and it does not find a solution. And there are typical reasons for that. And you can find those spots then easily when you turn off the heat computation calculation, the heat loss computation. A special option is consumer undersupply. That is when there is no sufficient pressure difference in a point. Typically, you need a certain pressure difference between supply and return in order to get the nominal capacity. And if you're falling short, then you have undersupply situation.
Okay.
Yeah, it's quite a special option.
A special option, right?
Yeah.
Yeah.
공급 차단은 그 어느 서플라이가 공급되고 사용시에 들어가는데 저거 클릭을 안 하면 그 미사일이 좀 깔아놓고 밸브 잘라놓고
Undersupply is when your network, for example, has too small diameters in pipes, and the demand is very high, and you have a high mass flow, then the pressure difference between supply and return, you get this situation.
Ah, I got it.
Yeah.
역차.
And then you get calls from your users. Oh,
yeah.
We are your user, but our water is not hot enough. We do not get enough mass flow to operate our heating.
Yeah. Okay. 역차.
Okay. Normally you deal especially with load factor and temperature setup. Then you have to have one pressure maintenance to define a point of fixed pressure in the system. And from the plant, when you operate it, the pressure maintenance is typically located where the supply stations are. It's the special, you have the expansion vessels and the pressure maintenance, and it's nothing we compute, but it just gives you a fixed point of pressure. Yeah. Then for all the controllable elements, we have to set up a control, and a pump, you can operate it with a control, or you can turn it off, or you can set it to a certain speed. When you set it to a certain speed, we need some characteristic data of the pump, so that we can look up on the pump curve, there is a given speed and the mass flow, so we can pick the pressure increase that is done by the pump. Let me draw the diagram. So if there is a pump curve, that is diagram mass flow, delta P of the pump, it's curved like this. And this is for a certain speed, let's say 1,500 CPM. It's what's the English term? I have to look up. It's yeah. And for a different speed of the pump, it goes down, and if it's higher, it shifts. This maximum point shifts a bit to the right. So this is for different speeds. And when we have a mass flow, and we know the speed, we can look up the delta P. So if you specify speed, we need such a curve.
Yeah.
If you do not specify this curve, we have some internal, and it will just suffice the control task. Okay. So here you pick one of the controls to operate the pump, and you can change the set point in this scenario. And for all the supply stations, we also need to know how to operate them. Most important is, of course, the supply temperature. And when you have multiple supply stations, you have some freedom to change the operation mode. But we always need one supply station that operates on load balance. What does now load balance mean? Looking at the network with a scenario, if we operate at 70% of nominal load, that will give us at a given temperature difference the mass flow. So if we say it's here, it's just, this is nominal 200 kilowatt, nominal, 70% means in this scenario 140 kilowatt. If the supply temperature is 110 Celsius degrees, 110, in the back return we have, let's say, 50, that's 60 Celsius degrees. So we can write this equation here, that the mass flow equals delta T. So this is the 60, this is the 140. The heat capacity, we can compute an average one from a thermodynamic library. So this way we get an estimation for the mass flow. Okay, with the mass flow, we can compute the heat loss. But the heat loss, we do not know upfront. The heat loss along a pipe depends on the mass flow through the pipe. So we know the demand, 140 kilowatts. But the supply station has to feed in 140 kilowatts plus a little bit. And that is to account for the heat loss in the network. And that is why we cannot specify as operation mode, hey, I tell you the heat load, if it's 140, we are missing the heat losses from via the surface. So I cannot put in 140. I cannot also not put in the flow rate or the mass flow because that information is dictated by the consumers. If I have one station, I need one that takes into account these, that can adjust to the requirements of flow. If we have multiple stations, we can operate one with a constant mass flow or with a constant heat, so that it feeds in a fraction of the required demand. But in a single case, for a single supply station, it's always load balance mode. If you try something different, see what happens. You get a red wrench indicating there is something wrong with the settings here. And that is, we know if there is only one supply station, you have to use the load balance mode. You are free to, nevertheless, run the computation. And you will get the error message. No supply with supply pressure mode for network balancing should be, it says supply pressure mode, oops, should be load balance mode for network balancing found. Okay, the message is a bit irritating. So I have to set it to load balance, then the message goes away. I now still get error messages, but basically the computation worked. It's just complaining about the state the network is in afterwards. But with this setting here, if I'm not using load balance, You see the status is it did not complete. Signaling with a symbol, and if it completes, it ends with errors, but it was able to finish the computation. Okay, was that okay and to understand?
Yeah.
Good. Okay, the remaining top pages are less important. We have one here called load prognosis, and I mentioned how we start the computation by estimating mass flows based on the demand requirements here, 70% for the station. If you have a lot of consumers in the network, you may want to use different diversity factors per consumers. A household is different from a business building, or maybe from an indoor pool. So to differentiate between them, there is an option to additionally apply here load factors on a per consumer group basis. So let me go to the board again, and let's say this is the typical, this is domestic heat. And here we have so this is business. And this is indoor pool. So in summer times, the indoor pool is probably at a diversity factor of 0. It's shut down. The business, when you want to compute it at weekends, probably also not working. Domestic always, but they may have different peak times and so on, and that is why you can break down the diversity factor on a per consumer group basis. And a consumer is always associated with such a group. And for such a group, you can define the diversity factor. That is where the load prognosis is for. Here in this case, seems I have only one group, but let me show what I mean when I go here. This is now consumer, has this group. Let me edit the consumer groups. I have another group here. I have one available at 100 Celsius supply temperature and 60 Celsius return temperature. Let me assign this one. And when the consumer group is used by any of the consumers, it will show up here. So I can give this, for example, name the business. It's just an arbitrary name. And this one, the other one, 150, let's call this domestic. And then you can assign different factors for domestic and business. And of course, when I now use this here and give it a factor of 0, it is like no demand in this point. By default, the return temperature that is specified in this consumer group, so the mouse is really slow, in the group, is used in the computation. in the scenario dialog box, in the column return temperature, you can override the value. So if you want to instead, for example, compute here with 58 Celsius degrees as return temperature, you enter 58. For this scenario, it would now use 58 instead of 50 Celsius degrees as return temperature.
그러니까 컨슈머 그룹에 50을 설정을 해놓더라도 칼큘레이션에서 58로 설정을 하면 58로 되는 건데. 오케이.
Okay, there are 3 remaining tabs. One is for isolation valves. An isolation valve is just that you shut a pipe. It is not half open, it's open or it's closed.
Yeah.
And it is, when you look at the pipe dialog box, it has one attribute that says can be isolated. Whenever a pipe has checked this attribute, can be isolated, it is listed as an isolation valve in the scenario dialog box. And such a pipe can be closed this way, or with a graphic tool, when you go to the pipe, you can open and close the pipe. So let me close the boxes here, and let me locate the one. That's this pipe here, and see we draw the isolation valve. So when it has the attribute can be isolated, it's with or it's without. And when it can be isolated, that was the message about. When I change it, the scenario settings need to adjust, because now it will be added to the settings whenever you add an isolation valve. By default, the pipe is open. And when I close the isolation valve, I would isolate this area in the network. It would not be supplied anymore. So I can use the graphic command here. Move onto the pipe and click, and it will close the supply and the return. Or when you click again, it will open.
Click this button.
Yeah.
You change.
Please click it here again. This one. Now click on it. No, that's okay. This is a graphic command. Okay, click this. Now pick it in the graphics. Click on this here. Yeah. Click again. With each click, it switches.
Is it off, right?
Off right now. Yeah. Red is it's closed. If you click it again.
Okay.
Yeah.
Double click.
Yeah, double click is 2 times it's so. Yeah.
There are so many variables because click like this.
It is useful if you have a lot of isolation valves in your system that you pick the right one from the list. You can do it in the list by double clicking here. It open closes. But as I pointed out at the beginning, if you only close this one and not this one, you get a computation, you get a problem. Let me show. If I open both, or now both are closed. Okay, I color code the temperature. It's now cold. That is why it's blue.
Yeah.
It is on ambient temperature. Now it is closed. I should mention one more attribute here in the drawing templates. That is the checkbox use style. Let me check this and show the effect. Then it gets a bit more prominent what happens. I redraw. When you check use style, whenever there is no result, it's dotted. That indicates better it is shut off, it has not been calculated. And when I open again screen, I recompute, it's now connected again with a solid line instead of a dashed line. But imagine I only close the supply part or the return part. Now I get a problem. Break with the network, cannot construct tree. This often means that something breaks the loop.
Yeah.
And that is then look through this list and you find the issue.
그냥 이거 랩을 설정하고 싶으면 이렇게 해보면 이건 노드가 중요한 행위거든요. 어차피 소리 없이 그냥 에디터를 한 다음에 이걸 해서 준비 안 써도
중간에
더블 클릭하면 켜지고 그러니까 여기서 클릭.
And the tool settings also apply here. The tool settings tell that it operates on supply and return at the same time. That is the safest way. Okay, now there are two remaining tabs. The design is grayed out. It's grayed out because on the general tab page we did not decide to use a design. So let me do the options first. That might be interesting for your networks as well. If you want that the drawing is automatically updated once a calculation completes, you can check the Update Drawings dialog box. That means you no longer have to recreate the drawing. And it will update all drawings that use calculation. So if you have 10 drawings with it, it will update 10 drawings. It will also take some time. This is why it's not activated by default. So for large networks with many drawings, maybe you do not want to use it. For our networks here at the training course, it is convenient to have the update drawings. You saw that in action when, let me uncheck and let me close the isolation valve. When I recompute, it's recomputed, but the drawing does not reflect the computational results yet. I have to redraw. Now it's in sync. And if you have many drawings, it takes also some time. If there are some 100 or maybe some 1,000 elements, it takes some time. And that is why we do not activate by default. But if I do this here, it is really convenient because I open again. Finished computation updates the drawings, and what you see on the screen is in sync with what you computed. Okay, finally, let's have a look at the top page for network design. And then I explain your question you dropped this morning on the board. So I switched from scenario calculation to scenario design. The difference is that we checked on the general top page the design mode. So I go to design, and once design mode is checked here, the top page for design is enabled. On the top page for design, you find the design scope, and I think that is what your question targets. It's the scope of pipes you want to design, and the limits to apply in the design. So if I want to design a portion of the network, I modify the design scope. As design scope, I can choose between the entire network or complete network, a selected zone. Initially, I showed the zone dialog. Every element is in a zone, and so you can pick the elements to design by zone. You can then design the pipes by pipe type. So if you want to redesign or check all pipes that are the N100, or finally you can break down to selected pipes. Whenever you have you are not on the entire network, you will find a list on the right side and some options to add elements into the scope. And those icons start graphical commands. So with a plus minus, you pick from the graphics. With a clear list, you remove everything from the list. And with the edit list icon, you get a list, now a list of all zones. And you can pick here some or more rows. When you dismiss the box, then the selected rows show up here in the list. In your case, you want to select individual pipes. So I use this option. The entire pipe list, maybe it's a lot of pipes, that's inconvenient. So again, do not use this, use the graphical command, and find again that you can have supply and return pipe picked at the same time you pick one in the graphics. So if I want to redesign the elements here at the end, every click will add the supply pipe and the return pipe. And let me compute. The design completed still with errors, but we'll have design results only for these 5 pipes. For a design mode, this this wizard to start the design analysis will be enabled. It's only when you have design mode that you get this option. Let me click it to start, and you can import the design results. And before the import is done, it compiles a list of which compares the actual pipe diameter with the design diameter. You access the list by clicking Display Evaluation of Design Results, this note symbol. And in my case, bad luck, we have no changes. It remains on DN40. I think that is because I designed with this criteria. Let me modify the design criteria and allow here much higher specific pressure losses and much higher speed, and rerun the design study. It will now recompute with these different limits, and I'm pretty sure we see now differences. Yes. So if we increase the limits, of course, all the pipes that are currently laid are too big. Therefore, the proposed pipe type is smaller and we get a green background. If it's the other way around and the pipe would be too small, it's indicated with a red color. In order to take over the proposed pipe types, you need to check this box to adopt the changes, and by pressing next we modify the pipe types here. So at present it's this is a DN50, these are DN40s. So let me do next. It adopts changes, and now this was changed to DN32. These steps are all undoable. So with edit undo, I can revert the operation. You get some clue looking at the display history. So this tells you the steps I performed now. So the pipe design visit was the most recently run operation. And if I undo it with this button, it goes to the redo stack. And when I look here with the tooltip again, we are back to DN40. Now the proposed pipe types and the design pipe type are different again. There is one interesting drawing template that has been set up for the design mode specifically, and that is when we design a pipe, we are interested in the diameter change. So what we did is we applied a color coding to pipes with a special table. We called it design. Let me have a look how the table is set up. The color table operates on the difference between design diameter and of course actual diameter. And if the difference is negative, it means that the design pipe is smaller. Okay, then it's green. That's good. If the pipe was too small, then the design pipe type is bigger, and design pipe type minus actual pipe diameter is positive, then it gets a red color. If it does not change, we use black. So with this setup of the color table, we can quickly identify how the network will change. And in our case, we did it only for these 5 pipes. So let me apply the design drawing template. With the design study, I just computed. And in this case, all the pipes are green. If I apply the suggestion and I adopt the pipe diameters, the changes go away, because now designed diameter and suggested, they just match. The situation is, I think, a little bit more. Well, yeah, let me keep this. Let me go back here to the original limits, and I do the entire network. And that gives, yeah, some better picture. So when I do the entire network, the pipes that start at the supply station, they should be laid out with bigger diameters, and here in some regions I can reduce diameters. So this is, yeah, that leads me to the final point, I think, before we do the lunch break. That is the methods to evaluate results. We saw that drawing templates are important, especially to get an impression of the situation in the entire network. Then for design, it's also important. We have the calculation log files that we'll revisit that and see what it means, what they tell us. And we have reports, HTML reports. And the very last icon in the calculation dialog box, it opens the report center. And it opens with the results that are for the design calculation. Note that the label of the computation is shown in the report center status bar. It is important because you can use the report center without the steady state calculation dialog box. What happens is when I switch to a different computation here, design, here it's design, when I switch to calculation, it will automatically switch computation dialog and it will switch the report center. So this way, I think you want to keep them in sync. We do that, and as a feedback, what we report about, it is shown in the status bar with the outcome of the most recent computation. So there were errors. The report center opens with a summary of the computation results. So it gives you information about the status that one ended with errors. It gives you the input data. So we operated at 70% load factor. It lists all the consumer groups with their load factors, ambient temperature, gives you then some statistical information about line length and network volume. Network volume is important for layout of the expansion vessels. So if you extend your network, at some point you want to modify the capacity of your expansion vessels to take account for the expansion. And then there is the heating balance, so heat input, heat load, and heat loss. Below this table, we show the list of all supply stations. And for the supply stations that one operates on load balance, it gets the mass flow, which depends on the demand of the network. Supply temperature, 110 Celsius degrees. And you can now have a look at individual elements when you use the navigation tree on the left-hand side in the dialog box. We labeled there the various element types in the network. So for example, you can have a look at your consumer stations. And the report is then organized by min, max values. And for min values, what's interesting, it's the differential pressure to know which station operates at the lowest pressure difference. And for the calculation I've done, okay, there are calculation errors, now you know why. That was an undesigned network. We computed, the computation was okay, but we found out that we have a negative pressure difference between supply and return in this situation. That is why it's complaining. maybe let me go to the example with the design. That's better. In the design, and our control was better. Our control said VB36 is operated at 0.5 bar. And looking at this list, this is indeed the consumer at the lowest pressure difference. If I would use VB129, then it would be controlled at 0.5 bar. Then this one will probably drop to 0.2. We can do so. And depending how sisHYD is configured, you will even get warnings if someone falls below 0.5. Okay, but this is for design. What else? For design, we can have a look at the pipes. And there is a special report for design results. It lists now all the pipes with the current diameter, the proposed diameter from the design study, the pipe length. If we provide lane cost information, we give the estimate of lane costs if you change to this diameter and you want to exchange the pipe. From these reports, you find hyperlinks. So whenever it's blue, it's a hyperlink. So you can open the pipe dialog box. In the pipe dialog box, you find here information about the price category. And this information is combined with, let's look at the pipe type. There is a prices tab. So this combination of the price category and the pipe type, that is the lookup for the price at level 1. If I would change here to price category 2, we would look up the price level 2. And that is how the computation here is done. These reports are configurable. So what we see here in the report center, you can influence. You can set up your own reports. You can especially then pick what columns you want to appear in this report. You saw from the drop-down list in the drawing there are too many attributes, and so we prepared the most important reports, what we think is interesting. But if you have questions or you want to have other reports, you would use the report designer instead of the report center to set up another report. You can modify the existing reports. So if you want to do this, so for the design report, let's say you want to also list the price category. Price category is a number between 1 and 6. And typically this means you divide your network in areas. If it's in the city, it is more costly, more expensive to lay because you have to dig the ground. If it's outside in the country, if it's green, it is easy. So you can assign your own categories 1 through 6. And let's say you want to list the categories in this report. You can do it with the report designer. Oops, that is the report center. If that one is open, you cannot access the report designer. When you shut down the report center, you can enter the designer, and the other way around. When designer is open, you cannot use the other one because you are about to change something. And the report about the design is, of course, in the category pipes. And this one is called design results. and it's important to know the report definition. A report is using a report definition, and then it defines sort order, how many columns you have, and the report type. When I want to modify the columns, I want to visit the report definition. Design result. And in design results, you get a list of attributes that are in the report. It's the name, the pipe type, design pipe type, length, investment, laying cost. On the right side, there are the labels in the report. On the left side, the attribute name in sisHYD. And by clicking the 6 attributes selected, you get access to the ellipsis button. From here, you pick what you want to show up in your report. And these are the current attributes, and I want to add the pricing category. There it is. Let me add it to the report, and maybe I want to move it up. So it's listed then as third column, and that's it. That's the modification. When I go back into the report center, pipe, design results, here we have pricing category. And yeah, the report center itself has some controls at the top of the dialog box. That is the paging size. So if you have huge networks, you can divide it into pages by 50 items. You are free to enter here any number. But in terms of retrieving the next page, it's more efficient to partition your report. There is a max number of rows to display. If you want to use this, to only get the top. And then we have 2 drop downs, one for the output. I guess one of the most important things is that we can export the current view to Excel. Should open here. Did I really hit? It's so slow. Come on. No other screen. Let's check my Excel is no longer working. Wow. Jeez. On your machine, I checked the Excel. I expect it to work. And mine was also working, so I wonder what's wrong. Okay. I cannot tell at the moment. Is yours working with Excel? Good. Use just output Excel current view. Yeah. Wow. Okay. Okay, that's it for the report center, and I initially mentioned that we tell about the correction factors and so on, and that is here also in pipes. You find their reports base data supply corrected, and this is the effective values that have been used for the length computation. That's the column corrected length. When the length correction factor has been applied to the length the pipe has in the pipe dialog box, it's the inner diameter, the corrected wall roughness, and the corrected heat transfer coefficient, and additional resistance factors are also listed. Another volume report is here about pipe volume. Some of our users, for example, used then pipes plus zone, and they were interested in the volume in a particular zone. So you can have your report with a zone column, just export all the pipes to Excel, and then you can have your own sums and so on. So we do not want to repeat what Excel offers. Therefore, we just export to it, and then it's easy to do the work there. Okay, I think that is basically how it works. After the lunch break, let me visit the selections and the profile plot. And I think then we are, then we did one pass through the application and go into the exercises. Okay.